Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
So we have 8 spotlight speakers. They have 3 minutes each. Please visit their posters once they're done.
Hi, my name is Dylan Foster. This is a joint work with Alexander Rocklin and Karthik Sridharan. So we study adaptive online learning algorithms. And these are online learning algorithms that are interesting because they can adapt to data that's nice or easy in some sense to achieve improved performance, but still maintain strong worst-case performance guarantees. And this includes algorithms that can encode a user's prior belief so that when data matches their belief, they get improved performance. Formally, we distinguish these algorithms from sort of typical online learning algorithms in terms of their regret bounds, which is our measure of performance. So your sort of typical online learning algorithm gives us a uniform regret bound where even though the bound is a function of data, or even though regret is a function of data, our upper bound is simply a function of the length t of the game that we play. Adaptive online learning algorithms, on the other hand, give us a regret bound that does depend on data and so can capture the nice properties I described before. So there's been a lot of work on adaptive online learning algorithms in recent years, but most of this is focused on specific algorithms. In our work, we sort of propose a VC or PAC style framework for studying adaptive online learning. In particular, we give sort of for a particular adaptive bound B, we look at whether or not there exists some algorithm achieving this bound in an information theoretic sense. So our work is a Minimax style analysis of achievability. We give sufficient and in many cases necessary conditions under which adaptive bounds can be achieved. So using our framework, someone can push a given adaptive bound through and either say, yes, this bound is achievable, or no, this bound is not achievable, but if we add some constant to it, we'll get a new bound that is achievable. Beyond looking at achievability, we look at going from bounds to algorithms. So given a bound, we can go to algorithms that achieve this bound using this framework that we call adaptive relaxations. We also derive new regret bounds for online learning. This includes sort of a new online PAC-Bayes style theorem and new bounds for online model selection that work in pretty generic settings. And we also give bounds for online supervised learning with predictable sequences, which allow us to sort of encode prior belief in behavior of our hypothesis class. And finally, we recover a pretty wide array of known adaptive regret bounds from literature. This includes small loss bounds, bounds for unconstrained linear optimization in Hilbert spaces, sort of regret to best versus regret to average style bounds, bounds for online learning with predictable sequences, and second order and quantile style bounds for experts. So if this sounds interesting to everyone, come have a look at our poster, which is number 100.
Hi, everyone. My name is Walid Krishan, and I'll give a brief overview of our paper on accelerated mirror descent in continuous and discrete time. And this is joint work with Alexandre Bayen and Peter Bartlett from UC Berkeley and QUT. So we consider the problem of minimizing a convex function with Lipschitz gradient on a convex constraint set. And what we show is how you can design accelerated dynamics in continuous time and then discretize them to obtain an accelerated first-order method for discrete optimization. And so in continuous time, what we do is essentially combine 2 ingredients. The first one is the ODE interpretation of Nesterov's method, and that's due to Su, Boyd, and Condes from last year. And the second ingredient is the mirror descent, the continuous time version of mirror descent, which is due to Nemirovsky and Yudin, which essentially lets you handle constraints by defining the dynamics on the dual space and then introducing this mirror map that maps the dual space to the constraint set. Okay, so by combining these two ideas, we define an energy function which is this v function here. It depends on a primal variable, a dual variable, and time. And then we design dynamics to make it decreasing over time. Okay? So as a consequence, we immediately obtain the 1 over t squared desired convergence rate. And in fact, the dynamics have this nice interpretation. So it's this figure on the right. So it tells you that there's a dual variable that follows gradient dynamics, but the gradient is multiplied by t. And then you have this mirror map that maps you to the primal space. And in the primal space, you do averaging. Okay? So it's a combination of dual dynamics and then averaging in the primal space. All right. And so in discrete time now, we show that by carefully discretizing this ODE, you can obtain a family of accelerated mirror descent algorithms that also achieve the same 1 over k squared rate. And what the discrete algorithm does is essentially at each iteration take 2 steps. One of them is this red, this update colored in red, which is a mirror descent update with increasing step size. And the second one is the green update, which can be anything from a gradient step or a proc step or a mirror step, but with constant step size. And then do a convex combination of those. Okay? And the way to show that this achieves the same 1 over k squared rate is to use the exact same Lyapunov function that we introduced in continuous time. So we make this connection between continuous and discrete time, which gives a lot of intuition of why acceleration works. And then we test this on a number of examples to show things like restarting heuristics, the effect of the different parameters in the algorithms, and so on. And so if this sounds interesting to you, I'd love to discuss the details, so come to our poster tonight. Thank you.
Hi, everyone. Title of poster is Empirical Localization of the Homogeneous Divergence on Discrete Sample Space. And I'm Takashi Takenouchi from Future University Hakodate, and this is a joint work with Takafumi Kanamori. And the purpose of this poster is to estimate parameter by solving this kind of optimization problem. L is a loss function, and P tilde is empirical distribution of the data set. And Q bar theta is a discrete probabilistic model, such as Boltzmann machine or restricted Boltzmann machine. And the difficulty of this kind of problem is caused by the calculation of the normalization constant. For example, Boltzmann machine has a normalization constant written like this. And this term is very difficult to calculate when the dimensionality of the input x is very large. So our motivation of our poster is we never want to calculate the normalization constant. And we employ 3 ideas to avoid the calculation of the normalization constant. First idea is unnormalized model without a normalization constant, written like this. And the second idea is homogeneous divergence. Homogeneous divergence is invariant against change of the magnitude of the function. So we can estimate the parameter with the unnormalized model. And the final idea is empirical localization. And this idea makes it possible to ignore the unobserved domain on sample space. So finally, we propose an estimator for the discrete model, which is derived from the convex loss function. And our proposed estimator can be constructed without calculation of the normalization constant. And our estimator is asymptotically consistent and efficient. I mean that estimator has the same efficiency with the MLE. So please visit poster 58. Thank you very much.
Hello everyone, I'm Jayadev Acharya. I'll talk about optimal testing for properties of discrete distributions. This is joint work with Konstantinos Daskalakis and Gautam Kamath. So we consider one of the most basic questions in statistics. Suppose you obtain samples from an unknown source or distribution P, and you want to know whether the data is coming from a particular source or family or a model of interest. For example, is the data coming from a monotone source, from a unimodal source? Or if it's a multivariate distribution, then are the marginals independent of each other? For example, suppose you observe a few examples from a three-dimensional categorical random variable denoting the gender, wealth, and voting preferences of individuals, and you may want to know whether these features are independent of each other. So as composite hypothesis testing, this problem has been extremely well studied in statistics for many decades now. And in the classical setup, the domain of the problem is fixed. The number of samples goes to infinity, and we study the error rates. So for many modern applications, the data set may be over an extremely large domain. It could be multivariate, and the number of samples is finite. And in these cases, one may want to study the optimal sample complexity, the computational efficiency for a small fixed error probability. And the question is, can we do it with number of samples that's only sublinear in the domain size? So we propose a unified framework that achieves the optimal sample complexity for a number of families of distributions, such as independence, monotonicity, log concavity, and so on. This unified framework is based on a modification to the well-known chi-square statistic that reduces the variance. And we also design efficient learning algorithms for all the classes that we want to test against. And one of the main results is that we can test many families of distributions with sample complexity that grows as only square root of the domain size. So if we have a domain of 1 million elements, then we need only 1,000 elements to be able to, 1,000 samples to be able to say something. So if we go back to the problem of testing independence of categorical random variables where each feature has k possibilities, then the domain size is k cubed, but we need only k to the 3/2 samples to test independence, for example. So please come to our poster number 9494. Thank you.
Hi, so I'm Yaron Singer from Harvard, and this is joint work with Jan Vondrak from IBM Research. So in this paper, we ask whether convex optimization is robust to mild errors. So suppose that instead of optimizing a convex function, you had access to a slightly erroneous version of the function. The question is whether you can optimize it approximately well. So in this example, we have a convex function that's depicted in blue and an erroneous version of it depicted in red. And now suppose that you start with a gradient descent algorithm on the erroneous version of it. The gradient descent algorithm starts somewhere and then immediately gets stuck in one of its the local optima of the erroneous function. So, and then returns the solution which is arbitrarily bad. So the moral is that gradient descent fails already for very, very small errors, right? Which is somewhat alarming, right? So now the question, the fact that gradient descent fails doesn't mean that any algorithm fails. So the question is whether we can design algorithms that are somehow robust to these small errors. Unfortunately, the answer is no. We show that very, very small errors lead to stark inapproximabilities. Basically, we show this for both the additive and the multiplicative error models when the error is as small as essentially 1/square root of n. 1/square root of n. And basically what we show is that for a series of very natural optimization problems in these various models, it would require exponentially many queries to get approximately good solutions. I can't go into the details of the proof, but I'll just give you some intuition. So basically what we do is for all these constructions, we construct two functions f and g so that on almost all the queries, these functions are very, very close. But on exponentially few queries, these functions are far. We then basically express the erroneous oracle through these functions and show that if we have access to this erroneous oracle, distinguishing between these two functions is somewhat hard. And this leads to the inapproximability results. So finally, just before I go, I just want to mention two results. So this result in convex optimization actually follows from a previous result that we have with Avinatam Chassidim on showing that the module optimization, is not robust to these sort of errors. But fortunately for some module optimization, we can show that we can get optimal approximation results with noisy oracles. Another result that I want to mention appeared in Cold this year, showing that if the error is on the order of 1 over n, then you can design algorithms that achieve good results. So in contrast to, in our model, we show that if you have error of 1 over square root of n, you have an inapproximability, but if the error is 1 over n, then you can design good algorithms. So that's it. Thanks.
Hello, everyone. I'm Mithun Chakraborty from Washington University in St. Louis, and I'm here today to present joint work with my advisor, Sanmay Das. So the question we address here is one that has been explored for some time across disciplines, ranging from machine learning to computational economics to more traditional economics and finance for that matter, which is that if a sequence of traders were to interact with the price-setting mechanism of a financial market, such as a prediction market, how would its price properties relate to the private beliefs held by these traders about the uncertain event on which the market is based? And most of the work in this vein that you will find involves some kind of equilibrium analysis of a market model with Bayesian learning agents. In this paper, however, we have adopted a different approach. We assume a myopic one-shot trader setting, and the only other assumption we make about trader behavior is that they follow a generic, smooth, risk-averse utility function. And we are agnostic to how the private beliefs of these traders are generated. We show that if such traders were to interact sequentially with the market scoring rule, which is a popular family of methods for implementing prediction markets, then the resulting price process is equivalent to an opinion pool, which is itself a standard belief aggregation procedure that has been studied for a long time in various fields such as political science. And this is the most general result we have. We also highlight a couple of special cases thereof, which are important in their own right. So the logarithmic market scoring rule, which is by far the most studied and the most used member of the market scoring rule family, in conjunction with the constant absolute risk aversion utility function class, which has no budget constraints, induces a logarithmic opinion pool, or in other words, a renormalized weighted geometric mean of the agent's personal probabilities. And the same market scoring rule, in the presence of a new budget-constrained utility function with decreasing absolute risk aversion, is equivalent to a linear opinion pool, or in other words, a weighted arithmetic mean of the agent's personal probabilities. And in these two special cases, we show that the market mechanism is equivalent to a Bayesian learner, even when the trader's beliefs are static. In the former case, the updated market price is equal to the posterior point probability of the forecast event, with the agent's belief serving as an observation with a well-defined likelihood structure. And in the latter case, the market's updated price is equal to the posterior expectation of a beta binomial inference, where the agent's belief acts as her private maximum likelihood estimate of the same probability. So that was an overview. If you're interested in the details, please stop by our poster. That's number 71. Thank you so much.
Hello, everyone. This is Jie Wang from University of Michigan. I'm presenting a multi-layer feature reduction for tree-structured group lasso via hierarchical projection. This is a joint work with Jieping Ye. Tree-structured group lasso is a powerful technique for feature selection when there's a hierarchical tree structure among the features. However, due to its highly complicated regularizer, solving the tree structure group lasso problem remains challenging, especially for large-scale applications. To deal with this, we propose a multi-layer feature reduction method to pre-identify the set of inactive nodes, which are groups of irrelevant features. Our method can be summarized in 4 steps. For the first step, we apply our method to test each node from the top level to the bottom level to detect the inactive nodes. For the second step, we remove the detected inactive nodes and all its descendants from the tree. For the third step, we remove all the features that are contained in the inactive nodes from the data. And finally, we solve the tree-structured group lasso problem on the reduced data. One appealing feature of our method is that the model learned on the reduced data is the same as the one learned on the full data. Our method is based on the geometric properties of the dual problem. Specifically, we have to decompose a given vector with respect to the dual feasible set that is induced by the tree structure. In other words, given the sum, we have to find all the summands. Even we only have 3 variables, we can see that the induced dual feasible set is very complex. One of our major contributions is that we show this decomposition problem admits a closed form solution by a hierarchical projection algorithm. A pillar to our method, to our result, is that we show the projection onto the sum of 2 convex sets can be decomposed into the sum of the projections onto these 2 convex sets, respectively, if one of them is a ball. Experiments show that our method is able to identify almost all of the inactive nodes, which leads to a speed up about 40-fold on data with about 500,000 variables. Without our method, the solver takes about 6 hours, which can be reduced to only 9 minutes if combined with our method. If you are interested, please stop by my poster number 63 tonight. Thank you.
Okay, last one. So I'm Tomer Koren, and this is a joint work with Ofer Dekel from Microsoft Research and Ronen Eldan from the Weizmann Institute. And it talks about bandit convex optimization, which is an online version of zero order or derivative-free optimization. And similarly to derivative-free optimization, we can only query function values, but the function also changes arbitrarily between queries. So it goes as follows. First, we have a convex function f1. We can query it at the point x1 and get to see the number f1 of x1. And we think about this value as the loss we suffer on the first round. Then, on the second round, there is a new function f2, which might have nothing to do with the previous function f1. We query it at the point x2 and get to see and suffer the loss f2 of x2 and get to see this number and this number only. So this goes on for t rounds, and our goal here is to do well, compared to the best fixed point x star had we played it constantly throughout the t rounds. This is what we call regret. So this nice problem was first studied in 2004 by Flaxman, Kalai, and McMahon, and was extensively studied since then. And despite of this effort, it is still open for more than a decade, even in the one-dimensional case. And when I say it's open, I mean there is a huge gap between the known algorithms and the information-theoretic lower bounds for this problem. Okay, so in this paper, our goal is to narrow this gap and bring algorithms closer to the lower bounds. And we do that by introducing a new bias variance trade-off of the gradient estimators used by previous algorithms for this problem. So previous algorithms used the queried function values to estimate gradients. These estimators are quite accurate. They have a low bias, but their variance is huge. We show a new trade-off that allows to substantially reduce this variance at the cost of a somewhat larger bias. And this trade-off turns out to work in our favor for smooth and convex loss functions, where the best regret was t to the 2/3, and whereas in our new algorithm gets regret of t to the 5/8, and you would have to trust me that 5/8 is really less than 2/3. Okay, so for the new algorithm, new bounds, and everything else, please come see us at the poster. Thanks.
Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.